Okay, so I
Okay,
can start, right?
we're ready. Sandeep will tell something
Perfect.
about CoinStack. Do you want to introduce yourself before getting started?
Um, Sorry, could you repeat?
Yeah, maybe it's nice if you introduce yourself before you start with the presentation.
Absolutely, absolutely. Yes, so thanks everyone for joining. My name is Sandeep Panta. I work at Trent Center at Georgia State University, and I'm the project manager for the COINSTAC software. So I'll be presenting about the tool today, talking about some new features, and introducing everything. So some of our collaborators and team members should be there. Um, Probably Dr. Vince Calhoun, Sergey Place, and Anthony Giuliano, and one of our coworker Dylan. So we can
I
have
don't
them.
see responses yet, but maybe some people walk in a bit later. Ah, I do see one response.
Perfect, perfect,
Okay.
awesome. So yeah, so the first part of the presentation, I will introduce CoinStack, and then I'll get into the latest algorithm that we have introduced in the framework, along with CoinStack Vault, and then I'll talk about the NVIDIA FLARE architecture for the next version of CoinStack, and then we'll get into some feedback Q&A in the last 20-25 minutes. So yeah, so I'll get started here. Okay, so
Can you bring
CoinStack
back up
is,
your slides? I had
sorry?
your slides just now and now I've lost them.
Okay, sorry, your voice is breaking up a little bit.
You had your slides up. You were sharing your screen before, and now I don't see your slides. Are you still sharing your screen?
Right, I am. So let me restart.
We can also look on our side if we can fix that if you're still sharing. One moment. Yes. Yeah. Okay. Yeah. It's fixed on our end. Thanks.
Perfect. Could you tell me if you're seeing the slide trends in brain research?
I am.
Perfect, perfect. Okay. So CoinStack is a platform for doing federated learning without sharing your raw or the original source data, thereby preserving privacy. So I will get into more detail about CoinStack. I'll give an overview of the trends in brain research and why this tool is helpful. So the overall goal of this presentation is to reintroduce CoinStack, promote the usage of this tool, and see how we can improve this. Okay. So the trends in brain research point to more data collection and more data processing capabilities due to increased hardware uh, power. But still, we are dealing with a lot of data sharing hurdles across the globe. So this is where CoinStack comes in. And we do have some federated learning tools in the field right now, but there is still a lot of learning curve because majority of them are command line tools that you have to learn how the code works, and there still requires a lot of manual collaboration between sites. And CoinStack has a user interface specifically for neuroimaging research. So we have solved a lot of problems that pertain to neuroimaging research. So COINSTAC stands for Collaborative Informatics and Neuroimaging Toolkit for Anonymous Computation. It's a long name. In short, it enables data analysis without sharing source data. So it allows for increased big data collaborative projects globally. Only the derivatives of the source data are shared between the client and the remote. So the source data always remains on the client's computer. So it's a comprehensive platform that allows federated learning, specifically designed for the field of neuroscience. And here's a sneak preview of the user interface. And first, user creates a consortium, which is like a project, and he sets up the pipeline. He picks a certain algorithm that he wants to run. In this case, it's regression on free surfer volumetric measurements. And he sets up the pipeline, and he invites other users in other sites to join this project. And he starts the pipeline. It's a standalone application that can run on Windows, Mac, and Linux. So it solves a lot of problems where you send multiple scripts to local sites and have them run specific set of scripts and then pull the data, etc. It's open source, free software. It runs inside Docker and Singularity containers. It currently, a lot of computations are using Python, but it can be programmed in any language because it's packaged inside Docker and Singularity containers. This is a sneak preview of the architecture. We can get into it in the feedback Q&A session if needed. Okay, so here's a small setup of a regression algorithm in COINSTAC framework. So each site will set up the model. In this case, it's volumetric measurements modeled against age and is control. And each site fits the model for their local data, sends it to the remote site. And again, here the source data remains at the client. Only the beta values for the fitted model are sent to the central. And a global fitted model is sent back to each site. It can be a simple average of the betas or using a gradient descent method. So here's the final fitted model. So that's typically how the algorithm works. We have done multiple projects using COINSTAC framework already. This one uses about 2,391 subjects across 14 sites spread out globally. And one of the main things we want to mention is that the results are comparable as if the data was pooled in a central location. So this way of running decentralized analysis is comparable to how you would run it on a single machine on pooled data. And we have done multiple comparisons using different algorithms. So in the last 1 year or two, we have learned various hurdles that are necessary to overcome in big data collaborative projects. And we have introduced support for Singularity because Docker cannot be installed on all the clusters. We've also introduced support for enabling network mounting and a lot of pre-processing algorithms for pre-processing structural data and functional data via command line and also the GUI. Here's another feature that we have introduced to overcome collaboration hurdles. So let's say that we have 5 sites across the globe that have different data sets. They want to do a project together. All the data needs to be organized in a standard format, and that has to be mapped so that the algorithm can be run on it. A COINSTAC Vault has pre-curated data set that is organized and it is available at all times so that users can use the Vault data and run computations on it. So here's a data set. that is run on Healthy Brain Network study, consists of 885 children. By the way, are you guys still able to hear me okay?
Yeah, we can hear you loud and clear.
Awesome, awesome. I need to check the time. Okay, perfect. We're still on track. Good. Okay, so I will show a small demo of how this COINSTAC Vault runs. So here we are logging into the COINSTAC application. You go to the Consortia tab, create a new consortia, give it a name. You're going to give the name of the pipeline that we are going to run on it. This will be a regression on free surfer volumes. So here we are adding the actual vault that has the pre-curated data set, and we add the algorithm that we want to run on the vault. And we have all this demographics and cognitive measurements that we can use. We're selecting the data type as the preset for volumetric measurements, and select any of the volumetric measurements from different brain regions. Now we save the pipeline. So the pipeline has the regression. We start the pipeline. So the pipeline is running. Once it's finished, you can see the results. And here you can see all the stats that were run on this specific data set. So that's a sample of how you can run a regression on a pre-curated vault data. Now you can also combine your local data with the existing vaults that we have on COINSTAC. So I'll go to the next slide, and I'll show you a sneak preview of how that works. So this is a data set that has 152 subjects from COBRA study, about half and half healthy controls versus patients. And these are all the demographics and cognitive measurements. And you can choose to exclude or include all of them. So here I'll show you the demo, how it runs. Giving it the name of the pipeline. In this case, you're running regression on the gray matter maps. So it's a voxel-wise regression. You can exclude some of the variables depending on your local data. If your local data only has certain variables that match with the vault, then you only want to include them. So now you can map your local data. And even if your variable names are different, you can drag and drop them according to the predefined pipeline setup. Now you start the pipeline. And once you see the results, there you go. So here are the local stats. So the beta values, voxel-wise beta values for age, is control, etc. And also you'll have global stats that use both the vol data and the local data. So it's a way to utilize more data. And we plan to have more vols in the future. And we also want to have more data sets from other organizations to be used as COINSTAC vols because it enhances collaborative projects. And here's an algorithm that I wanted to showcase. This is the latest algorithm that we have introduced in COINSTAC. It's a decentralized constraint source-based morphometry. It's essentially like an independent component analysis that is run on the gray matter maps from the structural MRI scans. So the goal is to extract maximally spatial independent sources and then use a linear regression to perform statistical analysis. And I can get into more detail and in the Q&A session about this as well, and Dr. Vince can also help answer questions. So source-based morphometry is good. It's a data-driven approach that is useful for studying the differences between patients and controls, essentially group differences. And we've implemented a federated version of this where the source data is not shared. So each site runs a constrained ICA. Constraint here means that we are using a predefined components for the ICA. And here we use 21 spatial components. So get into how it runs. Here we used a schizophrenia data set from 2 sites, approximately 50 subjects in each site. And this is how you set up the pipeline. And you select the template for the constrained ICA. And here we have a priori template that has 21 spatial components. And we have 2 users here. We run the pipeline and we get the local stats here. So here we have 21 components and their loading coefficients as they contribute to each subject. And we notice that the 17th component is reduced for patients, which is in line with what we would expect for schizophrenia study. So this is again reemphasizing that the decentralized version of the source-based morphometry is comparable to the pooled version. And now I'll briefly talk about NVIDIA FLARE. This is, I'm going to briefly check on the time. Okay, we're still good. Okay. So this is the latest feature that we are working on. It is sort of a redoing of our back-end architecture. So all the communication that happens between clients and remote servers was previously handled using COINSTAC framework. And NVIDIA FLARE has come out with its own federated platform that allows encrypted communication between the nodes and helps us do federated learning. So we have adapted NVIDIA FLARE architecture, and we still use COINSTAC GUI in the front end. In the back end, we're going to use NVIDIA FLARE to perform federated learning. And this is still in the works, but we expect to have product out with some algorithms in 2 months. And the reason for this is NVIDIA FLARE is actively being developed. It's a Python package, and it enhances also the algorithm developer experience. So it has a modular architecture. It's built for real world scenarios. And a lot of the things that um, the federated learning platform struggles with, the solutions have been put out by NVIDIA FLARE. And here's the algorithm developers experience as well. In case we want to develop new algorithms for a new project, say we're pursuing a grant and it requires a new algorithm that COINSTAC does not support. NVIDIA FLARE supports wrapping existing algorithms into the architecture in an easier way. And we have done a lot of that groundwork to provide documentation and development and tutorials on how to do that. And we've also revised the COINSTAC interface. The workflow still remains the same in terms of creating the consortia, inviting the users, and running the pipeline. But we have sort of improved based on our experience with different PIs, different organizations, and this is the new UI. So the new UI involves all the algorithms set up in one interface. And we can get into a little bit more of this as I proceed to the next slides. But essentially, you see the description of the pipeline here in the first piece, the settings for the pipeline, which can be edited to defaults or custom. And in the third tab, you see the notes that the consortium owner wants to communicate to the clients. And after this pipeline setup, you select the data directory where your data is, and you run the pipeline. And here is a small demo of how an algorithm can be wrapped inside NVIDIA FLARE architecture. And this is using a command line version of this. I'll just show a sneak preview of this. So we have created sort of a boilerplate template for wrapping existing computations and algorithms in the NVIDIA FLARE architecture. And what we run here is what will be available in the COINSTAC app as well. So it's much easier to develop computations under this new architecture. And this one is simply aggregating numbers from the remote clients on a central server and returning back the aggregated average. On the left, we see all the files that are created, the local average, and the global average. So this is just to demonstrate how it is to develop algorithms in the NVIDIA FLARE architecture. Okay. So we have a lot of existing computations that we would like for users to test for their projects. And their source code is made available on GitHub. And once you log into the COINSTAC app and go into the computations tab, you can see for each computation the link to the GitHub page. So the idea here is to promote COINSTAC because we feel like there's a lot of space in terms of big data collaboration projects across the globe. As more and more data is collected in the brain research space. So we want COINSTAC to be utilized more. And if people want to pursue grants as well to answer interesting research questions, and if that requires a new algorithm, we can collaborate with them. And we also want to integrate new computations as well into the code base. So there's a lot of ways to collaborate with us, and this is really an invite to uh, for researchers to participate with us. Here's our team. You may find some of our team members in this presentation or at OHBM. So feel free to connect with them and ask all the questions. We would love it if people use CoinStack more, or if we want to pursue grants together. So, and here's some of our team members. And I believe Dylan is available in this meeting as well. And he worked a lot on the NVIDIA FLARE architecture. Yeah, so thank you for listening to the presentation. And I'll open it up for some feedback, Q&A. And I would like to hear just any general feedback on how we can improve it, what are the current hurdles, and any new collaborative projects that we can pursue.
Thank you so much, Sandeep.
Thank you. Thanks a lot.
I'll stop the recording. Give me one moment.